Assalamualaikum, my name is Mo Adam. I will presenting part A, fundamental principles of counting for question number 1. The question is, a faculty is forming a student committee consisting of 3 members selected from 10 students. The role are president, vice president and secretary. And then I need to create our own scenario, my own scenario. Then the task is A. Explain whether your solution uses permutation or combination and justify your choice. B. In how many ways can the committee be performed if each role is assigned to a different students? And the last is C. Two particular students must be in the committee at the same time. How many valid committees can be formed? This is my new scenario. The scenario is a university is organizing an innovation and leadership camp. A committee of 3 members is to be selected from a group of 10 students to manage the event. The selected members will be assigned distinct roles: president, vice president, and secretary, where each role carries different responsibility. Question A. Explain whether your solution use permutation or combination and justify your choice. For this question, we use a permutation. Permutation is applied when the order of arrangement is important. In this case, the 3 selected students are not only chosen but also assigned to specific roles, which is president, vice president, and secretary. Each role is different and carries its own responsibility. This means that changing the position of the same students will produce a different outcome. For instance, if student A is assigned as president and student B as vice president, it is considered a different arrangement compared to student B being president and student A being vice president. Question B. Determine the number of different ways to select and assign 3 students from the 10 students into the role of president, vice president, and secretary. The answer is we have a 3 step. To find the total number of ways we assign the role step by using the fundamental principle of counting, where we multiply the number of choices at each stage. Step 1, choose the president. There are 10 students available, so there are 10 possible choices. Step 2, choose the vice president. After selecting the president, there are 9 students remaining, so there are 9 choices. Step 3, choose the secretary. After selecting 2 students, there are 8 students left, so there are 8 choices. Now multiply all the choices together. 10 multiply 9 multiply 8, so we get 720 ways. So means that there are 720 different ways to select and assign the 3 roles. Question C. Suppose 2 specific students are required to be part of the committee. Determine the number of ways to select the remaining member and assign all roles to the 3 students. Solution. In this situation, 2 students are already fixed in the committee, so we only need to determine how to complete the group and assign roles. We have also 3 steps. First step, select the remaining member. Since 2 students are already included, we need to choose 1 more student from the remaining 8 students. Step 2, assign roles to the 3 selected students. Now there are 3 students in the total, and they must be assigned to 3 different roles. The number of ways to a student is as we show now. And then step 3, find the total number of ways. Multiply the number of ways choose the last student with the number of ways to assign roles. And then this is the answer. There are 48 possible ways to form the committee when two specific students must be included. Thank you very much.
So on this slide, I am showing the original exercises given in the assignment. So the exercise will be a student will need to create a new scenario and also redesign the question within the task based on the example given. So the original example shown in the slide, which is about a company security system that uses a password made up of three uppercase letters and two digits with no repetition allowed. From an example of the assignment given, there are three given tasks which are as follows. Number one, which is the total number of valid password. The second one, which is the number of password that contain at least one vowel. And also lastly, how to answer the changes if the repetition is allowed. So the original question is a good example of counting because it combines both letter and also digits under a specific condition. So based on the example, I have redesigned the question into different but related to real life situation. Instead of passwords, I choose to use a vehicle registration license plate because the same counting concept can be applied clearly in the context. In this slide, present the new scenario that I have created. So in this new question, which is the Malaysia Road Transport Department introduced a license plate format consisting of four different uppercase letters followed by two different digits. So the digit must be appear at the end. So the pattern is letter, 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 and also digit, digit. For example, in this case, a possible plate could be A, B, C, D, 1, 2. But however, the four letters must all be different and the two digits must be also be different. From this scenario, there are three tasks has been given. First, we need to find the total number of the valid license plate. The second one, which is we need to find how many license plate have a vowel in the first position. And lastly, which is we modify the question by allowing the repetition and also compare the new result within the original cases. So on the next following slide, I will go through the solution one part at a time. So for question A, we want to find the total number of valid license plate that can be formed. So because the arrangement matters, so this will be a permutation problem. For example, A, B, C, D, 1, 2 is different from B, A, C, D, 1, 2. Even though the same letters and digits are used, the position of each character changes the license plate. So before calculating, let me explain the formula under the shown under the working. So the combination formula is we use which is NPR, which is equal N factorial divided by N minus R factorial. So in this case, the formula N means the total number of available items and R means the number of items selected and also arranged. While the letter P represents permutation, which means the arrangement where order matters. The exclamation mark means factorial. For example, 26 factorial means 36, 25 times 24, and so on until 1. So in this question, we don't need to expand the full factorial because the formula simplifies to the number of choices of each position. For the letters, N is 26 because there are 26 uppercase letters available, and the value of R is 4 because we need to select and arrange 4 letters into the position. So this is written as 36P4. But since repetition is not allowed, the choices decreases after each letter is used. So the first letter has to be 26 choices. The second one will have 35 choices, while the third will have 34 choices, and the fourth one which is we have 33 choices. Therefore, 26P4 is the same as 26 times 25 times 24 and times 23, which equals to 358,800 letters of arrangement. So next, we arrange the digits, whereby there are 10 digits from 0 to 9. So n is equals to 10. And also we need to arrange the digit. So r equals to 2. So this gives us which is 10p2. And again, because repetition is not allowed, the first digit has 10 choices and the second digit has 9 choices. So 10p2 is equal to 10 times 9 and also which equals to 90 digits arrangement. And also finally, we apply the product rule, see we multiply the number of letter arrangement by the number of digit arrangement because both parts are needed to form a one complete license plate. So 358,800 times with 90 equals to 32,292,000. Therefore, the total number of valid license plate is 32,292,200. So that will be the final answer for the question A. Now, we move on to the question B, where the first letter of the license plate must be a vowel. Let's look on the condition of the license plate that we produce as stated as follow. Number one, which is the four different uppercase letter, followed by two different digits, while no characters are repeated, and the digits must be at the end. And lastly, the license plate able to produce whereby have a vowel in the first position. So let's go on to step number one, which is arrange the vowel letters. The vowels are A, E, I, O, and U. So this means the first position has only 5 possible choices instead of 26. This condition reduces the total number of plates because the first character is restricted to vowels only. So the formula shown here is still the computation formula, NPR equals to n factorial divided by n minus r factorial. Here, n represents the total number of available choices, while r represents the number of positions that we are filling. P means permutation, and factorial means multiplying a number that went until 1. For the first letter, n is 5 because there are 5 vowels. The value of r is 1 because we are only to fill one position, which is the first letter. So this is written as 5p1. Since we are choosing one vowel for one position, 5p1 simply equals to 5. So for the next one, we go on step number 2. So to arrange the letter for alter the first vowel. After choosing the first vowel, repetition is not allowed, so that vowel cannot be used again. So this leaves 25 letters available for the remaining 3 letter position. For the second, third, and fourth letter, we use 25p3. In this part, n equals to 35 because 35 letters remain after the first vowel has been used. The value of r is 3 because we are still need to arrange 3 more letters. So when we expand it, 35p3 becomes 35 times 24 times 23. So this equal to 13,800 different arrangement for the remaining 3 letters. So for the later part of question B, we have 5 choices for the first vowel and 30,800 ways to arrange the next 3 letters. So the digit part is calculated on the next following slide. To complete question B, we now arrange the 2 digits. The formula used here is also the combination formula, NPR. In this digit part, N represents the total number of available digits, and R represents how many digits we are need to arrange. Since the digits are from 0 to 9, there are 10 digits in total, so N is equal to 10. Since the license plate need 2 digits at the end, R equals to 2. So we write this as 10p2. This means we are selecting and arranging 2 digits from 10 available digits. The order matters because a plate ending in 1-2 is different from plate ending in 2-1. Because repetition is not allowed, the first digit has 10 choices. After one digit has been used, the second digit has only 9 choices remaining. Therefore, 10p2 equals to 10 times 9, which gives 90 digits arrangement. Now, we combine all the parts using the product rule. We multiply 5 choices for the first vowel, 13,800,000 arrangement for the remaining letters, and 90 arrangement for the digits. So the calculation is 5 times 13,800 times 90, which equals to 6,210,000. Therefore, the number of valid license plate with a vowel in the first position is 6,210,000. This result is smaller than the question in A because the first letter is restricted to only 5 vowels instead of all 26 letters. We move on to the question T on the next following slide. Now we move to the question C, where repetition is allowed. So in this case, when repetition is allowed, the same letter or digit can be used more than once. For example, a plate such as A 1 1 will now be accepted. And this changes the accounting method because the number of choices does not decrease after each selection. The formula shown here is n to the power of r. In this formula, n means the number of available choices for each position, and r means the number of positions to be filled. We use this formula when repetition is allowed because every position has the same number of choices. So for the letter, there are 26 uppercase letters available. So n is equals to 26. There are 4 letter positions. So r is equals to 4. Therefore, the number of letter arrangement is 26 to the power of 4. So this means 26 we times to 26 times 26 times 26. Because each of the 4 letter position can use any of the 26 letters. So the answer is 456,976 different letter arrangement. So for the second part, which is the second step, which is the arrange of the digits. So for the digits, there are 10 digits from 0 to 9. So n is equals to 10. There are two digit positions, so r is equals to 2. Therefore, the number of digit arrangement is 10 to the power of 2. So this means 10 times 10, which equals to 100 digit arrangement. And finally, we apply the product rule again. We multiply 456,976 letter arrangements by 100 digit arrangement. So this will give us 45,697,600. Therefore, when the repetition is allowed, the total number of valid license plates increased to 45,697,600. This slide continues on the question C, but now we include the condition that the first letter must be vowel while repetition is allowed. The same repetition formula is used here, which is n to the power of r. In this case, n is the number of choices available for each position, and r is the number of positions being filled. Since repetition is allowed, the choices do not reduce from one position to the next. For the first one, the first letter must be a vowel. So there are 5 vowels. So n is equals to 5. Since we are only filling one position, r equals to 1. Therefore, this part is written as 5 to the power of 1, which equals to 5. Next, we fill the remaining 3 letter position. Because repetition is allowed, each of these positions can be filled with any of the 26 uppercase letters. So n is equals to 36, while r is equals to 3. This gives us 36 to the power of 3, which means 36 times with 36 times with 36. And the result which is 17,576 arrangement for the remaining 3 letters. For the digits, repetition is also allowed. There are 10 possible digits and 2 digits position. So n is equals to 10 and r equals to 2. That gives us 10 to the power of 2, which equals to 100. Now, we apply the product rule by multiplying all parts together, which is 5 times 17,576 times with 100. And the answer which is 8,788,000 license plate. So this means that when repetition is allowed, the first letter must be a vowel. The total number of possible license plate which is 8,788,000. And also it is higher than a non-repetition vowel because the remaining letters and digits can be reused. Finally, this slide compares the result with and without a repetition. So in this case, you can see here, without repetition, the total number of valid license plate which is 32,292,000. With repetition, it increases to 45,697,600. As for the case where the first letter is a vowel, the total which is 6,210,000 without repetition and 8,788,000 with repetition. So with this comparison shown an important counting principle whereby where repetition is allowed, every position keeps the full number of choices, so the total number of account becomes larger. Without repetition, the number of viable choices decreases after each of the selection. So in conclusion, the three main answers in this presentation are 32,282,000 for all valid place without repetition, 6,210,000 for the place with vowel in the first position, and 45,687,600 when repetition is allowed. Overall, this presentation shows how the permutation and the product rule can be used to solve the structured counting problems efficiently and also clearly. Thank you, and we move on to the next question.
Hello everyone, today I will be presenting question 3 from part B, which covers logical statement and truth tables. Okay, the logical statement we will be analyzing throughout this presentation is this statement. This presentation is structured into three main parts. First, we will construct the truth table. Second, we will classify the logical statement. And third, we will interpret it in a real-world context. Let's begin. Before we build the truth table, we first need to understand what each primitive statement represents in this problem. There are four variables defined as follows. First, P. The firewall is active. And next, Q. The password is weak. R. The user is authenticated. S. The user can access the system. These four variables are combined in logical statement if P and not Q, then R or S, which read if the firewall is active and the password is not weak, then the user is authenticated or the user can access the system. Okay, for question A, we identify all logical operators present in the statement and explain what each one means. The first operator is negation. Seen in Q, it reverses the true value of Q. If Q is true, then Q is false, and vice versa. The second is conjunction. And in P and Q, this is only true when both P and Q are true at the same time. Think of it as a logical AND. The third is disjunction, or in R or S, this is true whenever at least one of R or S is true. It represents a logical OR. The fourth is implication. This is the most important operator here. It is only false when the left side, called the antecedents, is true, but the right side, the consequence is false. Okay, for question A, we identify all logical operators present in the statement and explain what each one means. The first operator is negation. Seen in Q, it reverses the true value of Q. If Q is true, then Q is false, and vice versa. The second is conjunction. And in P and Q, this is only true when both P and Q are true at the same time. Think of it as a logical AND. The third is disjunction, or in R or S, this is true whenever at least one of R or S is true. It represents a logical OR. The fourth is implication. This is the most important operator here. It is only false when the left side, called the antecedents, is true, but the right side, the consequence is false. Okay, for question B, we need to determine whether the statement is a tautology, a contradiction, or a contingency. Okay, let's work through each possibility. Okay, a tautology requires all 16 rows in the final column to be true, but we found one row that is false, so it is not a tautology. A contradiction requires all 60 rows to be false, but 50 rows are true. So is it not a contradiction either? Therefore, the statement P and Q, R or S is a contingency. A contingency is a logical statement whose true value is not fixed. It can be either true or false, depend on the value assigned to its component variable. For question C, we translate this logical statement into a real-world context, specifically a computer security system. This system means if the firewall is active and the password is not weak, then the user should be authenticated or be able to access the system. In other words, when both security conditions are satisfied, an active firewall and a strong password, the system is expected to grant the user access. However, the statement becomes false in one specific scenario. The firewall is active, the password is strong, but the user is still neither authenticated nor able to access the system. This indicates a system-level failure, not a security breach, but a process or configuration issue within the system itself, despite all security requirements being met. Summarize the key findings from this presentation. For question A, we identify four logical operators in the statement: negation, conjunction, disjunction, and implication. We then construct the complete 16-row truth table following a systematic 5-step process. For question B, the statement P and R or S is classified as a contingency since the final column contains both true values, 15 rows, and one false value. It is neither a tautology nor a contradiction. For question C, in a real-world cybersecurity context, this statement tells us that a system meeting its security conditions should function correctly. If it does not, it signals an internal process failure rather than a security problem. That concludes my presentation. Thank you.
Hi everyone, I will present question 4, logical argument and validity. First, let us look at the given example with three compound statements. If a student studies, then they pass the exam. If a student passes the exam, they graduate. The student did not graduate. For my own scenario, I created 5 compound statements. Number 1, if an employee works hard, then they get good performance reviews. Number 2, if an employee gets good performance reviews, then they receive a bonus. Number 3, if an employee receive a bonus, then they are motivated. Number 4, if an employee is motivated, then they get promoted. Number 5, the employee did not get promoted. For my own scenario, I created 5 compound statements. Number 1, if an employee works hard, then they get good performance reviews. Number 2, if an employee gets good performance reviews, then they receive a bonus. Number 3, if an employee receive a bonus, then they are motivated. Number 4, if an employee is motivated, then they get promoted. Number 5, the employee did not get promoted. In symbolic logic, the scenario is represented as P means employee works hard, Q means employee gets good performance reviews, R means employees receive a bonus, S means employee is motivated, T means employees get promoted. The premises are if P then Q, if Q then R, if R then S, if S then T, not T. From these premises, the conclusion is not P, meaning the employee did not work hard. This argument is valid because by using the contrapositive rule step by step, each premise leads logically to the conclusion. We also test validity using the truth table. In every case where all premises are true, the conclusion not P is also true. Therefore, the argument is valid both by rules of inference by truth table.
By combining all these steps, we form a change. Not T implies not S, implies not R, implies not Q, implies not P. Therefore, the final conclusion is not P. This means the employee did not work hard. The rule used here is contrapositive rules. It states that if P implies Q, then not Q implies not P. By applying this rule repeatedly, we logically reach the conclusions, therefore the argument is valid. To confirm validity, we use a truth table. We check all possible values of P, Q, R, S, and T. We only focus on rows where all premises are true. On those cases, the conclusion is also true. Therefore, the argument is valid. Real-life application: this situation reflects real life in workplace. Hard work leads to good reviews, bonus, motivation, and promotions. If the employee is not promoted, we can logically trace backward to find the causes. In conclusion, the argument is valid. We provide this using simple logic, step-by-step reasoning, and through several verification. That's all.